Welcome, everyone, to our webinar, 4 Steps to Implement Governance as Code to Better Control Your Cloud. My name is Naor Paz, and I am the Director of Product at Firefly. In today's session, we'll explore how to effectively enforce governance policies when using infrastructure as code tools, such as Terraform, with a specific focus on AWS. We'll discuss 4 essential steps that will help you achieve better control, compliance, and consistency across your cloud environments. Whether you are a cloud engineer or responsible for an operational team, this webinar will provide you with valuable insights and practical examples to enhance your governance strategy. So let's dive in and discover how governance as code can help you better manage your cloud infrastructure. Before we get started, let's take a quick look at our agenda for today's webinar. We'll begin with a brief introduction to governance as code, where we'll define the concept and discuss its importance in the context of cloud infrastructure management. Next, we'll explore the benefits of implementing governance as code, highlighting how it can help you achieve better control, compliance, and consistency across your cloud environments. Then we'll dive into the 4 key steps to implement governance as code effectively: Terraform modules, code, plan, and cloud configurations. For each step, we'll discuss the benefits, challenges, and provide practical examples to illustrate how you can apply these concepts in your own infrastructure. By the end of this webinar, you'll have a clear understanding of how to implement governance as code to better manage your cloud infrastructure using Terraform and AWS. So let's get started with our introduction to governance as code. Governance as code is the practice of defining and enforcing governance policies using code, rather than manual processes or documentation. It ensures that policies are consistently applied across your infrastructure, reducing the risk of human error and making it easier to maintain compliance. While IAC tools like Terraform help you define and manage your infrastructure as code, governance as code takes it a step further by codifying the policies that govern your infrastructure. This can be achieved using tools and frameworks specifically designed for policy as code, such as Open Policy Agent, OPA, AWS config rules, or other open source tools. Some examples of governance policies can be codified, including security policies, such as access controls and encryption requirements, compliance policies, such as data retention and privacy regulations, and cost optimization policies, such as resource tagging and usage limits. Now let's explore some of the key benefits governance as code offers for managing cloud infrastructure. 1. Reduced risk misconfigurations. By defining your governance policies as code, you can ensure that they are consistently applied across all your environments, reducing the risk of misconfigurations. Automated policy enforcement. With governance as code, you can automate the enforcement of your policies, reducing the need for manual interventions and freeing up your team to focus on more strategic tasks. Version controlled and auditable policies. When your governance policies are defined as code, they become version controlled and easily auditable, providing better visibility into your infrastructure changes and making it easier to demonstrate compliance. Rapid issue remediation. In the event of a security incident or a compliance breach, having your governance policies defined as code can help you quickly identify and remediate the issue by leveraging automation and version control. Scalable and flexible governance. Governance as code allows you to scale your governance policies alongside your infrastructure, ensuring they remain relevant and effective as your cloud environment grows and evolves. By leveraging these benefits, governance as code can help you achieve a more secure, compliant, and efficient cloud infrastructure. In the next slide, we'll introduce the 4 key steps to implementing governance as code effectively. Why 4 crucial steps? When it comes to implementing governance as code in the context of infrastructure provisioning, it's crucial to understand the full life cycle and the unique governance challenges and opportunities presented at each stage. As depicted in the diagram, we can break down the process into 4 distinct phases: modules, code, plan, and cloud. By focusing on compliance and best practices at each stage, we can ensure a comprehensive and effective approach to governance. Let's start with modules. Building reusable templates. Modules serve as the foundation of our infrastructure provisioning process. Created by cloud engineers, these templates encapsulate best practices and consistent configurations for specific resource types or services. Modules can be nested and composed together to build more complex structures. The key principle behind modules is immutability and reusability. By leveraging variables, modules offer a high degree of customization while maintaining their integrity. Large organizations can have hundreds of engineers utilizing the same module, such as an EC2 module for creating virtual machines on AWS. Specific teams can further enhance modules by wrapping them up to cater to specific applications or service types. Multiple resources can be coupled together into a single module, forming a cohesive unit. At this stage, compliance is enforced at the template level, ensuring that best practices are baked into the modules themselves. Number 2, code, HCL, if we talk about Terraform, defining specific infrastructure. So in the second phase, we transition from templates to actual code written in HCL. This is where we express our intent to create specific cloud infrastructure for a particular purpose. Although we're still in the coding phase, without any API calls to the cloud or runtime validations, we start to become more granular about what we want to create. The code typically calls one or more modules referencing the reusable templates we defined earlier. Variables within the modules are now assigned specific values, representing the desired configuration of the resources. This increased specificity, allows for deeper scrutiny of potential misconfigurations. Number 3 is our plan, bridging code and reality. The third phase is where our code begins to interact with the actual cloud environment. By running a plan, we compare our code against the current state of the cloud and obtain a detailed list of the changes that will be applied. It's important to note that infrastructure as code follows a declarative approach. Until a plan is executed, we don't have a clear picture of what will change. The plan output represents the exact intended modifications to our cloud infrastructure, providing a final opportunity for review before any changes are made. During this stage, real API calls are sent to the cloud, resolving any runtime or plan time dependencies, such as data sources for AMI images. And the fourth step, cloud resource configurations, managing live resources. The fourth and final phase assumes that we have successfully applied our code and the changes have been made to the cloud infrastructure. In real-world scenarios, cloud environments can experience drift or manual changes through the cloud console, what we used to call ClickOps. To maintain compliance, it's essential to regularly scan the cloud configurations and compare them against our defined policies. Additionally, certain properties and IDs of resources are only known after the apply stage, as they are determined by the cloud provider during the provisioning process. In the following sections, we will dive deeper into each of these four stages, exploring specific examples and best practices to ensure unified and effective governance as code throughout the infrastructure provisioning lifecycle. Let's delve into the first phase, modules, or as I like to put it, shifting as left as possible. On the right side of the slide, you'll find an example of an AWS VPC resource within a module template file named maintf. Notice the variables. Their values remain undefined until the module is invoked. As we discussed earlier, modules are versatile and not bound to any specific infrastructure. In fact, the creators of these modules sometimes do not use them directly. For instance, a central platform team might develop modules that are then utilized by specific cloud or development teams. In this example, the S3 server-side encryption is enabled by default, ensuring compliance with security best practices right out of the box. However, while default encryption enhances security, it may not always suit every use case. For greater flexibility, we've designed a module to allow toggling encryption on or off. This adaptability makes the module more generic and versatile, capable of fitting into a wider range of deployment scenarios. Users can easily modify the encryption settings to either enable or disable it based on their specific requirements, ensuring that the module can be tailored to meet different security standards or operational policies. In these examples, we've introduced a toggle that allows the encryption to be enabled or disabled. This introduces a variable element into the compliant status of the module. It can't be fully determined until the module is actually called and the Boolean variable's value is set. As a result, the responsibility for ensuring compliance is shifted to the phase where the module is utilized. It's very important. This emphasizes the need for robust governance mechanisms in later stages. Remember, we talked about the four stages. In later stages to verify and enforce compliance once the actual configuration parameters are known. In this example, we discuss how to manage bucket versioning in our S3 module with a dual approach, using a toggle to enable or disable versioning and implementing a validation block to enforce that versioning is enabled. This setup allows users the flexibility to choose their configuration while ensuring that versioning cannot be inadvertently disabled. The reason for combining both a toggle and a validation block is to balance user autonomy with compliance requirements. The toggle gives users the control to enable versioning as needed, which can be beneficial for environments where versioning may introduce unnecessary overhead. Meanwhile, the validation block acts as a safeguard, ensuring that in environments where data integrity and recoverability are critical, versioning must remain enabled, thus preventing potential configuration errors that could lead to data loss. This approach ensures that the module adheres to strict governance standards while still offering flexibility. As you can see, we can also adapt our validation to do exactly that. Today, I'm also excited to introduce Kix by Checkmarx, a leading open source tool that enhances infrastructure compliance. Kix leverages the Open Policy Agent, OPA, tool by parsing HCL into JSON and scanning it with Rego policies. On this slide, you'll see an example of a Rego rule that Kix uses. Implementing Kix in your development pipeline, especially as an automated check within pull requests, ensures that your Terraform modules remain compliant. This integration can serve as a crucial safeguard, automatically scanning and validating changes to ensure they meet your organization's compliance standards before being merged. By automating compliance checks with KICS, we can significantly enhance security and governance in our cloud infrastructure. At Firefly, we also leverage KICS. In summary, keep in mind, any misconfiguration in your reusable module can turn your cloud infrastructure into Swiss cheese, riddled with vulnerabilities. Let's discuss code scanning. While similar to scanning Terraform modules, scanning direct Terraform resources gives us more detailed information, particularly when filling in variable values for module calls. This allows us to use proprietary policies or open source tools for more comprehensive scans, which we'll briefly demonstrate. In this slide, we examine a Terraform setup where a security group is deployed via a module, while an EC2 instance is created directly within the primary configuration. This instance then references the security group defined by the module. It's important to note that using a module to deploy the security group alone does not ensure compliance for the directly created EC2 instance. Thus, scanning the full code base with a comprehensive tool is essential to ensure that all resources, including our EC2 instance, meet compliance standards. For example, to enforce policies on the instance type, we can use Rego, the language utilized by Open Policy Agent, CNCF project, to specify and check these constraints. Let's look at a sample Rego rule that ensures EC2 instances are not of an XL type, which might be overly large and expensive for our needs. This Rego code snippet defines a policy that flags any EC2 instance configured to that size, providing an actionable warning within the policy evaluation outputs. This ensures we adhere to size and cost considerations in our cloud infrastructure. Let's show some other tools. Checkov by Bridgecrew, Python-based rules to scan Terraform code for enhanced governance, recently acquired by Palo Alto Networks. It's a tool worth considering. Some other tools worth mentioning are Tenable TerraScan and TFSec from Aqua Security. They can both help you scan code, and I welcome you to compare and choose your favorite. In this slide, we focus on an S3 model implementation that includes a Boolean variable for encryption and sets the ACL to private. When applying governance policies that assess the ACL settings, these policies may not directly evaluate the private setting within the module itself, potentially misclassifying it as compliant without deeper analysis. However, tools like KICS, which are designed to scan IAC, face limitations with custom modules that are not sourced from public registry. Since KICS may not have direct mappings between variable names and the actual properties of AWS resources in such modules, it cannot definitively determine compliance. This is particularly true for properties like ACL, where the actual implementation details are crucial for security. You can always create custom policies for your specific modules, but this will be a significant investment. To address these gaps, additional steps are necessary. Scanning the Terraform plan as a last pre-deployment prevention measure becomes essential. Now let's talk about the plan phase, which represents the actual changes or intended changes to your cloud environment and serves as the final checkpoint before implementation. In the Terraform plan phase, the proposed changes are outlined, allowing you to review and verify them before applying. This helps ensure the changes align with your expectations and avoid any unintended modifications. The plan phase provides a detailed preview of what will be added, changed, or destroyed, giving you full visibility and control over your infrastructure updates. Policies can be enforced on the plan output in a JSON format with various tools. Open Policy Agent with special policies, also KICS we just talked about that can parse a plan output and run a policy, enforce a policy, ensuring that the actual changes remain compliant after compiling all variables and data sources. Remember, we have variables. We have some data sources that are unknown until we actually run the plan. As you can see on the left, assigning variables directly in Terraform is just one method. You can also use tfvars file, environment variables, CLI flags. This approach keeps variable values out of the code and calculates them during the Terraform plan. Hence, it's crucial to scan the plan to understand the configuration changes to your cloud. With tools like Kix, you can sometimes scan both the code and variables by referencing the variables file to the tool, though this isn't always possible. Here's a data source, which is determined only at plan time. When searching for an AMI image ID for a VM, you only get the ID after the plan. Once real Cloud API requests are made, this means that any policy validation related to this or any other data source results can only be performed during the plan phase. It's crucial to understand this timing to ensure accurate compliance and validation processes. Another example of a data source is retrieving information about a specific VPC by using the AWS VPC data source. You can fetch details about a VPC based on its ID or tags. This information, like the AMI, is only available at plan time and is essential for referencing existing infrastructure components accurately in your Terraform configuration. Last but not least, cloud configurations must also be checked for several reasons. Some information is only available after the apply phase. If you remember the plans showing some properties known after apply. So this means certain configurations and resource details can only be verified once they're actually applied or deployed to your cloud, such as an IP address or other stuff. Manual changes, also known as ClickUps or drifts, will not be detected in earlier phases. Therefore, it is essential to scan the actual configuration upon a change. This can be triggered by events from services like CloudTrail, ensuring that any deviations from the intended state are promptly identified and addressed. These checks are crucial for maintaining the integrity and security of your cloud infrastructure. Imagine that you have a fully compliant module and you scan your module and your code that calls the module and the plan, and then someone comes and makes a manual change to your resource and breaks the policy, right? So this is very, very important. To ensure continuous compliance and governance in our AWS environments, we can leverage AWS config rules. It's just an example. These rules allow us to automatically check the configuration of resources. This is an example of a rule that is defined to check whether EC2 instances are of a specific type, such as T2 micro. This rule continuously monitors EC2 instances and ensures they comply with the specified type, helping maintain consistent and secure configurations. Remember, the tools we talked about before are not intended for cloud configurations. They can work for modules, Terraform code, Terraform plan, but you probably need different tools for that. Another example is Cloud Custodian. It's also a CNCF project, flexible tool used to enforce compliance, governance, and security across cloud resources. It allows us to define policies that can automatically audit and take action on AWS resources based on specific criteria. This is an example of a cloud custodian policy that ensures all EC2 instances have a specific tag. Tagging policies are very important, but again, you have to enforce at all stages. This is an environment tag. So again, there are many other tools used to do this. Custom policies, compliance packages for different frameworks. But again, you have to find a way to also enforce the same policies, unified policy across all the stages we talked about. So let's recap what we covered today. We discussed what governance as code is and why it is crucial for your cloud environment. We outlined the 4 steps necessary to enforce a unified policy across modules, code, plan, and cloud configurations. We reviewed some open source and cloud native tools that can help you implement these policies. And as a part of that, we looked at real world examples from AWS and Terraform. We mentioned S3s and encryptions, EC2s, instance types, environments, and tags. By the way, if you don't feel like building all of that from scratch, feel free to check Firefly for free at firefly.ai. And now let's have a Q&A session. Feel free to drop any questions as you have. And for those who watch the recording, feel free to send more questions to my email, Naor, that's Naor, at firefly.ai. So I see we don't have questions on the chat. We'll give it another minute or so. And in the meantime, I will tell you that what we do at Firefly is actually help you implement all of that. So I really encourage you to test. You can start for free in our website at firefly.ai, and we help you enforce unified policies across those stages. I think it's interesting to see how many incidents happen when you even leave just one step out of the equation. We see that with our customers all the time. Oh, yes, I didn't scan the plan. I did scan the code. I did scan the module. Or on the other hand, you have a problem with the module and you just replicate the problem across all the instances of that module. So again, it's not as easy to implement, especially if you are doing it yourself with open source tools. It will take you some time and resources for your team. Your backlogs are large enough. So it's always good to consider a product to do it for you. Anyway, I think we don't have questions for now. Again, feel free to send me questions now or at firefly.ai. And that's the time to thank you all for your participation in our webinar today. It's been a pleasure, and I wish you all a great rest of your week. Thank you so much.